Tonight, we're going to explore something that will fundamentally change how you understand reality itself. We're going to discover that time, the one constant you've relied upon your entire life, the steady tick of seconds and minutes and hours that has accompanied every moment of your existence, is not what you think it is. Time is flexible. Time is malleable. Time can stretch and compress. Time can speed up and slow down depending on how fast you're moving and where you are in a gravitational field. This isn't science fiction. This isn't speculation. This is proven, experimentally verified fact. And by the end of tonight's journey, you're going to understand exactly how we know this, what it means, and why it changes everything about how we perceive the universe and our place within it. Before we begin, if you enjoy these deep explorations into the mysteries of our universe, a quick like or subscribe would really help the channel grow. Now let's step into the strange reality where time itself bends to the laws of physics. Let's start with something simple. Right now, as you're listening to this, time is passing. 1 second follows another in perfect rhythm. The clock on your wall ticks forward. Your phone displays the time, changing minute by minute. Everything in your experience tells you that time is universal, that it flows at the same rate for everyone, everywhere. 1 second for you is 1 second for someone across the world. 1 second for an astronaut in space. 1 second for every person who has ever lived or will ever live. But that's wrong. Completely, fundamentally wrong. Time does not flow at the same rate for everyone. The second you just experienced might have been longer or shorter than the second someone else experienced, depending on your relative motion and position in a gravitational field. This isn't a small correction or a tiny adjustment. In the right circumstances, the difference can be dramatic. One person might experience years, passing while another experiences only hours. One twin might return from a journey to find their sibling aged decades while they aged barely at all. This phenomenon is called time dilation, and it's one of the most thoroughly tested, rigorously confirmed predictions in all of physics. We're not talking about a theoretical possibility or a mathematical curiosity. We're talking about something we can measure, something we have to account for in everyday technology, something that affects you right now even if you don't realize it. The story begins in 1905 with a 26-year-old patent clerk in Bern, Switzerland. Albert Einstein wasn't working at a university. He wasn't part of the scientific establishment. He was spending his days evaluating patent applications for electromagnetic devices, but in his spare time, he was thinking about light, motion, and the nature of time itself. Einstein was troubled by something that seemed like a contradiction. Physics at the time said that light was a wave traveling through a medium called the luminiferous ether, much like sound waves travel through air. If that were true, then the speed of light should depend on how you're moving relative to the ether. If you're moving toward a light source, the light should reach you faster. If you're moving away, it should reach you slower. Just like sound from an approaching ambulance reaches you faster than sound from a receding one. But experiments kept showing something strange. No matter how you moved, no matter what your velocity, light always traveled at exactly the same speed, about 300,000 kilometers per second, or roughly 186,000 miles per second. It didn't matter if you were rushing toward the light source or fleeing from it. The speed was always the same. This made no sense. How could something always move at the same speed regardless of the observer's motion? If a car passes you going 100 kilometers per hour and you're traveling in the same direction at 80 kilometers per hour, the car is only moving 20 kilometers per hour faster than you from your perspective. That's basic physics. But light doesn't work that way. Light always moves at 300,000 kilometers per second relative to you, no matter how fast you're going. Einstein realized that for this to be true, something else had to give, and that something was our understanding of space and time. He published his special theory of relativity in 1905, and it revolutionized physics. The paper was titled "On the Electrodynamics of Moving Bodies." Those pages contained ideas that would reshape our understanding of reality. Einstein started with two simple postulates. First, the laws of physics are the same in all inertial reference frames. An inertial reference frame is just a perspective where you're not accelerating, where you're either at rest or moving at a constant velocity. If you're in a smoothly moving train with the curtains closed, there's no experiment you can do that will tell you whether you're moving or standing still. Physics works the same either way. Second, the speed of light in vacuum is the same for all observers, regardless of their motion relative to the light source. This was the weird experimental result that needed explaining. From these two postulates, Einstein derived something extraordinary. If the speed of light is always constant, and if physics is the same in all reference frames, then time and space themselves must be relative. Time must flow at different rates depending on your motion. Space must stretch and compress. These aren't just mathematical tricks or convenient fictions, they're real physical effects. Here's how it works. Imagine a simple clock. A pulse of light bounces between two mirrors. Each round trip is one tick of the clock. If the mirrors are 1 meter apart and light travels at 300,000 kilometers per second, each tick takes a very specific amount of time. Now imagine this clock is on a spaceship moving past you at high speed. From your perspective, watching from outside, the light doesn't just bounce straight up and down. It has to travel diagonally because the clock is moving sideways as the light bounces. The light has farther to travel to complete each round trip. But remember, the speed of light is constant. It's always 300,000 kilometers per second, regardless of the motion of the clock. So if the light has farther to travel, it must take more time to complete each round trip. The clock ticks slower. Time on the moving spaceship passes more slowly than time from your stationary perspective. This is time dilation. Moving clocks run slow, and it's not just light clocks. All clocks run slow when they're moving. Mechanical clocks, atomic clocks, biological clocks, even the aging of your cells. Time itself is passing more slowly for the moving object. The amount of time dilation depends on speed. At everyday speeds, walking or driving or even flying in an airplane, the effect is vanishingly small. But as you approach the speed of light, it becomes dramatic. The relationship is described by what's called the Lorentz factor, named after Hendrik Lorentz, who worked out the mathematics before Einstein explained the physics. The Lorentz factor is written as gamma. It equals 1 divided by the square root of 1 minus velocity squared divided by the speed of light squared. When you're moving slowly compared to light speed, this factor is very close to 1, meaning almost no time dilation. But as your velocity approaches the speed of light, the denominator approaches 0, and gamma shoots toward infinity. Time dilation becomes extreme. Let's put some numbers to this. If you're traveling at 10% of the speed of light, about 30,000 kilometers per second, the Lorentz factor is about 1.005. Your time is running about half of 1% slower than someone at rest, barely noticeable. At 50% of light speed, gamma is about 1.15. Your time is running about 15% slower. Now it's getting significant. At 90% of light speed, gamma is about 2.29. For every hour you experience, someone at rest experiences 2.29 hours. Time is running more than twice as slow for you. At 99% of light speed, gamma is about 7.09. Your clock ticks 7 times slower. At 99.9%, gamma is about 22.4. Now the difference is dramatic, and as you asymptotically approach light speed, gamma approaches infinity. Time dilation becomes infinite. This is why nothing with mass can actually reach light speed. To do so would require infinite energy and would cause time to stop completely from the perspective of outside observers. But here's the crucial thing to understand. This isn't a trick or an illusion. The moving person really does experience less time passing. If you could somehow travel at high speed and return, you really would have aged less than someone who stayed behind. This is real, and we've proven it. The first hints of experimental confirmation came in the 1930s and 1940s from observations of cosmic rays. Cosmic rays are high-energy particles, mostly protons, that strike Earth's upper atmosphere from space. When these particles collide with atoms in the atmosphere, they create showers of new particles. Among these are particles called muons. Muons are similar to electrons, but about 200 times heavier. They're unstable. Left to themselves, they decay into an electron and a pair of neutrinos. The average muon lifetime is about 2.2 microseconds. That's 2.2 millionths of a second. Here's the problem. Muons are created high in the atmosphere, typically around 15 to 20 kilometers up. They travel toward Earth at speeds very close to the speed of light, often around 99.8% of light speed or faster. Even at light speed, it would take light about 67 microseconds to travel 20 kilometers. But muons only live for 2.2 microseconds on average. Do the math. If time were absolute, if there were no time dilation, a muon traveling at 99.8% of light speed would cover only about 660 meters before decaying. They're created 20,000 meters up. Almost none of them should reach the ground. We should detect essentially zero muons at sea level, but that's not what we observe. We detect lots of muons at sea level, thousands per square meter per minute, far more than should be possible if muons only lived for 2.2 microseconds in all reference frames. The explanation is time dilation. From our perspective on the ground, the muons are moving at extremely high speed. Their clocks are running slow. The 2.2 microsecond lifetime is measured in the muon's own reference frame, its proper time. But from Earth's reference frame, time dilation extends this lifetime dramatically. At 99.8% of light speed, the Lorentz factor is about 15.8. A muon that lives for 2.2 microseconds in its own frame lives for about 34.8 microseconds in Earth's frame. That's enough time to travel over 10 kilometers at near light speed. Many muons make it to sea level before decaying. This was observed experimentally as early as 1941 by physicists Bruno Rossi and David Hall. They measured muon intensities at different altitudes and found exactly the distribution predicted by time dilation. The moving muons really were living longer from our perspective because time really was passing more slowly for them. In 1962, a more precise experiment was conducted by David Frisch and James Smith. They measured moon flux at the summit of Mount Washington in New Hampshire at an altitude of about 1,917 meters above sea level, and compared it to measurements at sea level in Cambridge, Massachusetts. They measured the muons' velocities, allowing them to calculate the expected time dilation. The results matched the predictions of special relativity with excellent precision. These experiments have been repeated many times since with ever greater accuracy. Particle physics experiments routinely see time dilation in particle decays. Particles traveling at high speeds in accelerators live longer, exactly as predicted by relativity. It's not a subtle effect. It's dramatic and unmistakable. But perhaps the most famous direct test of time dilation came in 1971 with an experiment conducted by Joseph Haffel and Richard Keating. Haffel was a physicist at Washington University in St. Louis. Keating was an astronomer at the United States Naval Observatory. They decided to test time dilation using the most precise clocks then available, cesium beam atomic clocks. Atomic clocks work by measuring the oscillations of atoms between different energy levels. The frequency of these oscillations is incredibly stable, much more stable than any mechanical clock. Cesium atomic clocks in the 1970s could keep time to within about 10 nanoseconds per day. That's 10 billionths of a second. With that kind of precision, you could potentially detect the tiny time dilation effects from an airplane journey. Haffel and Keating obtained funding from the Office of Naval Research. The budget was tiny by research standards, only about $8,000. Most of that, about $7,600, was spent on airplane tickets. They bought 8 round-the-world tickets on commercial flights. 2 seats on each flight were reserved for Mr. Clock. They flew 4 cesium atomic clocks eastward around the world on regularly scheduled commercial airline flights, then returned them to Washington. Then they did the same westward. The clocks were compared before and after each journey to reference clocks at the Naval Observatory that remained stationary. The predictions were clear. Flying eastward in the same direction as Earth's rotation, the clocks would be moving faster relative to the center of the Earth than the stationary clocks at the observatory. Special relativity predicted they should tick slower and lose time. But there was another effect to consider. The airplane clocks would be at higher altitude farther from Earth's center, experiencing slightly weaker gravity. General relativity predicted that clocks in weaker gravitational fields tick faster. This gravitational effect would cause the clocks to gain time. For eastward flights, the two effects partially oppose each other. The velocity effect causes time loss. The altitude effect causes time gain. The predictions, accounting for the actual flight paths and altitudes, were that the eastward flying clocks should lose about 40 nanoseconds, give or take 23 nanoseconds of uncertainty. For westward flights, the situation is different. Flying westward means traveling against Earth's rotation, So the airplane velocity relative to Earth's center is actually lower than the stationary clocks at the observatory. This means the velocity effect causes the flying clocks to tick faster and gain time. The altitude effect also causes gain. Both effects work in the same direction. The prediction was a gain of about 275 nanoseconds, give or take 21 nanoseconds. The results were clear. The eastward flying clocks lost 59 nanoseconds, give or take 10 nanoseconds. The westward flying clocks gained 273 nanoseconds, give or take 7 nanoseconds. Both results matched the predictions within the experimental uncertainties. Time dilation was real. You could put atomic clocks on commercial airplanes, fly them around the world, and measure the difference. Time really does pass at different rates for objects in motion. The Raphael-Keating experiment has been repeated many times since, with greater precision. In 1996, the National Physical Laboratory in the United Kingdom repeated the experiment on the 25th anniversary of the original, using more precise atomic clocks on flights from London to Washington and back. They measured a time gain of 39 nanoseconds compared to a prediction of 39.8 nanoseconds. Nearly perfect agreement. In 2005, physicist Tom van Bach conducted a gravitational time dilation experiment by taking portable cesium clocks to Mount Rainier in Washington state, reaching an elevation of about 5,400 feet. The clocks showed a measurable time difference compared to reference clocks at sea level, consistent with general relativity's predictions for gravitational time dilation. Even more precise measurements have been made in controlled laboratory settings. In 2010, physicists at the National Institute of Standards and Technology used optical atomic clocks to measure time dilation at speeds of less than 36 kilometers per hour, about 10 meters per second. At walking speed, they could detect the tiny time dilation effect. They also compared clocks at different heights, separated by only about 33 centimeters, about a foot, and measured the gravitational time dilation between them. These aren't contrived experiments designed to barely detect an obscure effect. Time dilation has real practical consequences that affect technology we use every day. The most important example is the Global Positioning System, GPS. GPS works by precisely timing signals from satellites. Your GPS receiver picks up signals from at least 4 satellites orbiting Earth. Each satellite broadcasts its position and the exact time the signal was sent, as measured by atomic clocks on the satellite. Your receiver compares the times from multiple satellites to calculate how far away each one is. From those distances and the known positions of the satellites, it can triangulate your location. The precision required is extraordinary. GPS aims to locate you to within a few meters. Light travels at 300,000 kilometers per second, which means it travels about 30 centimeters in 1 nanosecond. To achieve few-meter accuracy, the satellite clocks must be synchronized to within about 20 to 30 nanoseconds. But the satellites are moving, and they're at high altitude. Both special and general relativity affect them. The GPS satellites orbit at an altitude of about 20,200 kilometers above Earth's surface. They complete 2 orbits per day, traveling at approximately 14,000 kilometers per hour, about 3.9 kilometers per second. Special relativity says that because the satellites are moving at this velocity relative to observers on Earth, their clocks should tick slower. The calculation shows that special relativity causes the satellite clocks to lose about 7.2 microseconds per day compared to stationary clocks on Earth. But general relativity says that because the satellites are at higher altitude, farther from Earth's center in a weaker gravitational field, their clocks should tick faster. The calculation shows that general relativity causes the satellite clocks to gain about 45.8 microseconds per day. The net effect is that the satellite clocks gain about 38.6 microseconds per day relative to clocks on the ground. That's 38,600 nanoseconds per day. If this effect weren't corrected, GPS would fail catastrophically. Position errors would accumulate at a rate of about 10 kilometers per day. After just a few minutes, GPS would be useless for navigation. The system would tell you you're in the wrong city, then the wrong state, then eventually give you positions hundreds or thousands of kilometers from your actual location. So the engineers who designed GPS had to account for relativity. They did this in a clever way. Before the satellites are launched, the atomic clocks on board are set to tick at a slightly different frequency than ground clocks. Instead of 10.23 megahertz, they're set to 10.22999999543 megahertz. This compensates for most of the relativistic effect. Once in orbit, these pre-adjusted clocks tick at approximately the same rate as clocks on the ground. There are additional corrections that have to be made continuously because satellite orbits aren't perfectly circular. As satellites move closer to or farther from Earth in their elliptical orbits, both the velocity and the gravitational field strength change slightly, creating small variations in the time dilation. These are calculated based on each satellite's precise orbital position and velocity, and are transmitted to GPS receivers as part of the satellite signal. GPS is a working, practical demonstration that relativity is real and necessary. Millions of people use GPS every day without realizing they're depending on Einstein's equations from 1905 and 1915 working correctly. If relativity were wrong, GPS wouldn't work. But it does work spectacularly well because relativity is right. But special relativity is only half the story. Einstein's 1905 theory dealt with uniform motion, with inertial reference frames moving at constant velocity relative to each other. It didn't include acceleration, and it didn't include gravity. That came 10 years later in 1915 with Einstein's general theory of relativity. This was a much deeper and more radical theory. Special relativity modified our understanding of space and time. General relativity completely reconceptualized them. In general relativity, gravity is not a force pulling objects together. Instead, gravity is the curvature of space-time itself, caused by the presence of mass and energy. Massive objects warp the fabric of space-time around them, and other objects move along the curved paths in this warped space-time. What we perceive as gravitational attraction is really just objects following straight lines, called geodesics, through curved space-time. One of the key predictions of general relativity is gravitational time dilation. Time passes more slowly in stronger gravitational fields. A clock sitting on Earth's surface, deep in Earth's gravitational field, ticks more slowly than a clock far from Earth in weaker gravity. It's not that gravity affects the clock mechanism. time itself is passing more slowly. The effect is quantified by a fairly simple formula. The fractional difference in time rates between two locations is approximately equal to the difference in gravitational potential divided by the speed of light squared on Earth's surface compared to infinity. The effect is about 7 parts in 10, followed by 9 zeros. Very small, but measurable with precise enough clocks. The first terrestrial test of gravitational time dilation was conducted in 1959 and 1960 by physicists Robert Pound and Glenn Rebka at Harvard University. They used an effect called the Moosbauer effect, which allows gamma rays to be emitted and absorbed with extremely precise frequencies. The experiment took place in the Jefferson Physical Laboratory at Harvard, using a tower 22.6 meters tall. A source of gamma rays was placed at the bottom of the tower. A detector was placed at the top. According to general relativity, as the gamma rays traveled upward, climbing against Earth's gravitational field, they should lose a tiny amount of energy. This would shift their frequency to slightly lower values, a gravitational redshift. The effect over 22.6 meters is minuscule, only about 2.46 parts in 1,000 trillion. But with the Moosbauer effect, it was just barely detectable. Pound and Rebka mounted their gamma ray source on a loudspeaker that could vibrate it up and down at controlled speeds. This created a Doppler shift in the gamma ray frequency, which they could use to compensate for the gravitational shift. By carefully tuning the vibration speed, they could find the exact frequency where the detector absorbed the maximum number of gamma rays. The results confirmed Einstein's prediction. The gravitational redshift was measured to be about 2.56 parts in 1,000 trillion, with an uncertainty of about 0.25 parts in 1,000 trillion. This matched the theoretical prediction within the measurement error. Gravitational time dilation was real. The experiment was refined in subsequent years. By 1964, Pound and his colleague Joseph Snyder had improved the accuracy to about 1%. More recent experiments using better clocks and longer baselines have confirmed gravitational time dilation with extraordinary precision. In 2020, physicists in Japan used optical lattice clocks, some of the most precise timekeepers ever built, to measure gravitational time dilation between the base and the observation floor of Tokyo Skytree, a tower 450 meters tall. The clocks were so accurate that they could detect the difference in time flow from this modest height difference with excellent precision. In 2022, physicists at JILA, a joint institute of the National Institute of Standards and Technology and the University of Colorado, measured gravitational time dilation at the millimeter scale. They used a cloud of ultra-cold strontium atoms trapped in an optical lattice. The cloud was only about 1 millimeter tall, but the atomic clock was so precise that it could detect the difference in gravitational time dilation between the top and bottom of this tiny sample. The atoms at the bottom, closer to Earth, ticked measurably slower than the atoms at the top, just 1 millimeter higher. These aren't academic exercises. Understanding gravitational time dilation is crucial for precision timekeeping, navigation, and geodesy. The fact that time passes at different rates at different altitudes means that if you want to synchronize clocks around the world to extreme precision, you need to account for their elevations. The International Atomic Time Standard maintained by a network of atomic clocks around the world, includes corrections for the altitude of each clock. The practical applications are expanding. As clocks become more precise, they can be used to measure tiny differences in gravitational potential, which corresponds to measuring elevation with extraordinary accuracy. Portable optical atomic clocks could be used to map Earth's gravitational field with unprecedented detail, detecting underground cavities or deposits or magma chambers by the subtle changes in gravitational potential they create. General relativity becomes truly extreme near black holes. A black hole is what remains after a very massive star exhausts its nuclear fuel and collapses. If the star is massive enough, nothing can stop the collapse. The stellar core compresses smaller and smaller, and the gravitational field at its surface grows stronger and stronger. Eventually, gravity becomes so intense that even light cannot escape. A boundary forms called the event horizon. Anything that crosses the event horizon, even light itself, cannot get back out. It's trapped forever. The radius of this event horizon is called the Schwarzschild radius, named after Karl Schwarzschild, who derived the solution to Einstein's equations for a non-rotating black hole. For a non-rotating black hole, the Schwarzschild radius is equal to twice the mass times Newton's gravitational constant, divided by the speed of light squared. For a black hole with the mass of our Sun, the Schwarzschild radius would be about 3 kilometers. Compress the Sun down to a sphere 6 kilometers in diameter, and it would become a black hole. Near a black hole, gravitational time dilation becomes extreme. As you approach the event horizon, time slows more and more relative to observers far away. At the event horizon itself, from the perspective of a distant observer, time dilation becomes infinite. Time appears to stop completely. Imagine watching an astronaut fall toward a black hole. As they get closer to the event horizon, you see them moving more and more slowly. The light from them becomes increasingly redshifted, shifting toward redder wavelengths. They become dimmer and dimmer as the light struggles to climb out of the deepening gravitational well. From your distant perspective, the astronaut never quite reaches the event horizon. They asymptotically approach it, slowing more and more, fading to invisibility, but never crossing. But from the astronaut's perspective, nothing special happens at the event horizon. They fall right through in a finite amount of their own proper time. There's no barrier, no wall, no dramatic moment. They simply cross the horizon and continue falling toward the singularity at the black hole's center. The extreme time dilation is only relative to distant observers, not experienced by the falling astronaut. This has profound implications. From the perspective of the outside universe, an object falling into a black hole never quite crosses the event horizon. It appears to freeze just at the surface, fading away over time. But from the object's own perspective, it falls through and is destroyed. Both perspectives are valid. This is the strange nature of relativity. We've observed evidence of extreme time dilation near black holes. Astronomers have been watching stars orbit the supermassive black hole at the center of our Milky Way galaxy, called Sagittarius A star. This black hole has a mass of about 4.3 million times the mass of our Sun. Stars orbit it in elliptical paths that bring them very close to the black hole at periapsis, the closest point in their orbit. One star, designated S2, has been tracked for over 2 decades. Its orbit brings it within about 17 light hours of the black hole's event horizon, traveling at speeds exceeding 25 million kilometers per hour at its closest approach, about 2.5% of the speed of light. As S2 makes its close approach, astronomers can measure the redshift of light from the star, and they can measure small deviations in its orbit caused by relativistic effects. In 2018, S2 made a close approach and passed through periapsis. Observations confirmed that the star's light was gravitationally redshifted exactly as predicted by general relativity. This was the first detection of gravitational redshift from a star orbiting a black hole. Direct confirmation of Einstein's predictions in an extreme gravitational environment. In 2019, astronomers released the first ever image of a black hole's event horizon, or rather the shadow it casts. The Event Horizon Telescope, a global network of radio telescopes, working together, imaged the supermassive black hole at the center of the galaxy Messier 87. The image showed a dark central region, the black hole's shadow, surrounded by a bright ring of hot gas, orbiting at nearly the speed of light. The size and shape of this ring matched the predictions of general relativity with remarkable accuracy. In 2022, the same team released an image of Sagittarius A star, the black hole at the center of our own galaxy. Again, the observations matched general relativity's predictions. The shadow was the right size. The light was bent the right amount. Time dilation and gravitational effects were exactly as Einstein's equations said they should be. These aren't just abstract confirmations of theory. They demonstrate that our understanding of time dilation is correct even in the most extreme gravitational environments in the universe. Let's consider one of the most famous thought experiments in relativity, the twin paradox. Imagine two twins, Alice and Bob. Alice stays on Earth. Bob boards a spaceship and travels at very high speed to a distant star and back. From Earth's perspective, Bob is moving at high speed. Time dilation means his clock ticks slower. When he returns, he should be younger than Alice. But from Bob's perspective, he's at rest in his spaceship, and it's Alice and Earth that are moving away at high speed. Shouldn't Alice's clock tick slower from Bob's perspective? When they reunite, should Alice be younger? This seems like a paradox. Who is actually younger? The resolution is that the situation is not symmetric. Bob accelerates when he starts his journey, when he turns around at the distant star, and when he stops back at Earth. Acceleration breaks the symmetry. Alice remains in an inertial reference frame the whole time. Bob does not. The accelerations Bob experiences mean his reference frame is not inertial during those times, and the predictions of special relativity, which applies only to inertial frames, don't directly apply during the acceleration phases. When you properly account for the acceleration phases, or when you use general relativity, which can handle acceleration, the answer is clear. Bob really is younger when he returns. The effect is not symmetric. The twin who travels and accelerates really does age less than the twin who stays home. This has been tested experimentally. In 1977, at the European Organization for Nuclear Research, physicists stored muons in a magnetic storage ring, forcing them to travel in a circle at high speed. The muons were accelerating constantly as they circled the ring. Their lifetimes, as measured in the laboratory, were extended by a factor matching the time dilation predicted for their speed, even though they were accelerating. This confirmed that time dilation applies to accelerating reference frames, just as special relativity and general relativity predict. The twin paradox is not actually a paradox, it's a real effect. If you could travel at high speed to a distant star and return, you really would return younger than someone who stayed on Earth. The laws of physics genuinely allow for this kind of one-way time travel into the future. You could travel decades or centuries into Earth's future by your own clock, while experiencing only a few years of travel time. Of course, the practical barriers are enormous. Accelerating to speeds close to light speed requires immense amounts of energy. The faster you want to go, the more energy you need, and the requirement approaches infinity as you approach light speed. With current technology, we can't get anywhere close, but the physics allows it in principle. Astronauts on the International Space Station experience a tiny version of this effect. They're orbiting Earth at about 28,000 kilometers per hour. This causes time dilation that makes their clocks tick slightly slower, but they're also at higher altitude in weaker gravity, which makes their clocks tick slightly faster. Velocity effect dominates slightly, so overall they age fractionally slower than people on the ground. Astronaut Scott Kelly spent 340 consecutive days on the ISS from 2015 to 2016. During that time, he aged slightly less than he would have on Earth's surface due to the combination of velocity and gravitational effects. His twin brother Mark, also an astronaut, but remaining on Earth during Scott's mission, aged slightly more. The difference is measured in milliseconds, tiny but real and measurable with precise enough clocks. Time dilation also appears at cosmological scales. When we observe distant supernovae, we see them evolving in slow motion. Supernovae brighten over a period of weeks, reach peak brightness, then fade over several months. But distant supernovae, billions of light years away, take longer to brighten and fade. Their light curves are stretched out in time. This is cosmological time dilation. It's caused by the expansion of the universe. As space expands, thus, wavelengths of light traveling through that space are stretched, redshifted, but time intervals are stretched too. Events in distant galaxies appear to happen in slow motion from our perspective because the expansion of space has stretched the intervals between those events. This effect was first clearly observed in the 1990s in studies of distant Type 1, a supernovae. The supernovae are used as standard candles to measure cosmic distances. Astronomers noticed that the most distant supernovae not only appeared dimmer, as expected for their distance, but also evolved more slowly. The time dilation factor matched the redshift factor, exactly as predicted by general relativity in an expanding universe. This observation was one of several pieces of evidence confirming that the universe really is expanding, and that general relativity correctly describes the large-scale structure of space-time. The philosophical implications of time dilation are profound. We tend to think of time as absolute and universal, a river flowing at the same rate for everyone, carrying all events along in a single sequence. But relativity shows this picture is wrong. Time is relative. Different observers can disagree about the order of events, about how much time elapsed between events, even about whether two events are simultaneous. Simultaneity is relative. If two events occur at the same time in one reference frame, They might not occur at the same time in another reference frame, moving relative to the first. There is no absolute present moment shared by all observers. The concept of now is observer dependent. This raises deep questions about the nature of reality. If different observers have different presents, different nows, what does that mean for the passage of time itself? Some physicists and philosophers argue that all moments in time are equally real, that the past, present, and future all exist in a four-dimensional space-time block. The flow of time, the sensation that the present moment is special and moving forward, might be an illusion of consciousness rather than a fundamental feature of reality. This is called the block universe view. It's a controversial interpretation, and not all physicists accept it, but it's motivated by the relativity of simultaneity. If there's no universal present, if different observers slice space-time into space and time differently, then perhaps all of space-time exists at once, and the flow of time is just our subjective experience of moving along our individual world lines through that four-dimensional structure. Other implications concern causality. Relativity preserves causality in a specific sense. Cause must precede effect in all reference frames. No signal can travel faster than light, which ensures the causal order is preserved. If event A causes event B, then A will occur before B in all reference frames. Different observers might measure different time intervals between A and B, but they'll all agree on the causal order. This is why faster-than-light travel would be so problematic. If you could send signals faster than light, you could set up situations where cause and effect become scrambled. Different observers would disagree on the causal order. You could potentially send messages into your own past, creating paradoxes. General relativity strictly forbids this through its cosmic censorship and causality protection theorems, at least in physically reasonable spacetimes. Time dilation connects deeply to the equivalence principle, one of Einstein's key insights in developing general relativity. The equivalence principle states that acceleration and gravity are locally indistinguishable. If you're in an enclosed room with no windows, there's no experiment you can do to tell whether the room is sitting on Earth's surface, experiencing gravitational acceleration, or whether the room is in deep space being accelerated upward by a rocket at 9.8 meters per second squared. The two situations are physically equivalent. This equivalence is why gravitational time dilation and velocity time dilation are connected. An accelerating observer experiences time dilation relative to an inertial observer. By the equivalence principle, an observer in a gravitational field should also experience time dilation. This was one of the arguments Einstein used to predict gravitational time dilation before general relativity was fully developed. Research into time dilation continues at the frontiers of physics. One area is the development of ever more precise atomic clocks. Optical lattice clocks, which use optical frequencies rather than microwave frequencies, can now achieve fractional frequency uncertainties below 1 part in 10 to the 18th power. These clocks are so accurate that they would gain or lose less than 1 second over the age of the universe. With such precision, clocks can detect gravitational time dilation over height differences of just a centimeter. They could map gravitational potential differences across a city, detecting underground structures or monitoring volcanic activity by the tiny changes in local gravity. They could test general relativity in new regimes, looking for tiny deviations that might hint at new physics. In 2024 and 2025, physicists are continuing to develop next-generation optical clocks using different atomic species and exploring new techniques like quantum entanglement that could potentially beat the standard quantum limit on measurement precision. If successful, these clocks might eventually detect effects at the boundary between quantum mechanics and general relativity, potentially probing how gravity and quantum physics interact in ways we don't yet fully understand. There are also proposals to use ultra-precise clocks in space-based experiments. By placing optical lattice clocks on the International Space Station or on satellites in different orbits, physicists could test general relativity in microgravity environments with unprecedented precision. They could look for subtle violations of Einstein's equations that might reveal deeper theories of gravity. Another area of research involves studying time dilation effects on quantum systems. Quantum mechanics describes particles in terms of wave functions, probability distributions that evolve according to the Schrödinger equation. But general relativity describes space-time as curved by mass and energy. How do these two frameworks fit together? One approach is to study quantum systems in gravitational fields, looking at how time dilation affects quantum coherence and entanglement. In 2022, experiments at GILA used optical lattice clocks to study this question. They prepared clouds of atoms in quantum superpositions of states and measured how the atom's quantum properties were affected by the gravitational time dilation across the cloud. This is at the cutting edge of what's called quantum gravity phenomenology, using precision measurements to probe the interface between quantum mechanics and gravity. Some of the strangest implications of time dilation appear in thought experiments about black holes. The information paradox asks what happens to information when matter falls into a black hole. Quantum mechanics says information is never destroyed, but if something falls past the event horizon, the information appears lost to the outside universe forever. Stephen Hawking's discovery that black holes emit radiation, now called Hawking radiation, partially addressed this. The radiation carries away energy, causing the black hole to slowly evaporate. Over immense timescales, the black hole might disappear completely, but the Hawking radiation appears thermal, random, containing no information about what fell in. Where did the information go? This paradox has driven decades of theoretical research. The current leading idea is that information is somehow encoded in subtle correlations in the Hawking radiation, recoverable in principle, though not in practice. This requires quantum mechanics and gravity to interact in complex ways we don't yet fully understand. Time dilation near the black hole horizon plays a crucial role in these considerations because it affects how information propagates and how entanglement behaves near the horizon. The study of time dilation has also led to deeper understanding of black hole thermodynamics and entropy. The event horizon of a black hole has an entropy proportional to its surface area. This entropy is connected to information and to quantum properties of space-time. The extreme time dilation at the horizon is intimately tied to these thermodynamic properties. Let's consider what time dilation means for interstellar travel. If we could build a spacecraft capable of traveling at significant fractions of light speed, time dilation would become crucial for long journeys. Imagine a spacecraft traveling to Proxima Centauri, the nearest star beyond our Sun, at a distance of 4.24 light years. If the spacecraft could somehow travel at 90% of light speed, the trip would take 4.7 years from Earth's perspective. But for the travelers on board, experiencing time dilation with a Lorentz factor of 2.29, the trip would take only about 2.06 years. If the spacecraft could reach 99% of light speed, the journey would take 4.28 years from Earth, but only about 0.6 years, about 7 months for the travelers. At 99.9% of light speed, the Earth time is 4.24 years, but the traveler time drops to only about 0.19 years, roughly 2 months. The more distant the destination, the more dramatic the effect. Alpha Centauri is about 4 light years away. Barnard's star is about 6 light years. The center of the Milky Way is about 27,000 light years away. At speeds close enough to light speed, the time dilation factor can become arbitrarily large. In principle, if you could accelerate to speeds close enough to light speed, you could travel to any point in the observable universe within your own lifetime. The galaxy could be traversed in years or decades of ship time, even though tens of thousands or millions of years would pass on Earth. This is sometimes called the cosmic speed limit loophole. You can't travel faster than light, but you can experience arbitrarily compressed time during your journey, allowing you to subjectively reach distant destinations in reasonable time frames. The catch is that everyone you left behind will have aged enormously or died by the time you return. You'd be traveling into Earth's far future. The energy requirements make this impractical with foreseeable technology. To accelerate a spacecraft to 90% of light speed requires roughly 2.3 times the spacecraft's rest mass energy. That's an enormous amount of energy, equivalent to completely converting more than twice the spacecraft's mass into pure energy. Current technology can't come close, but the physics allows it. There's no law of nature forbidding this kind of time-dilated interstellar travel. It's an engineering challenge, not a fundamental impossibility. Some theoretical proposals for future spacecraft involve antimatter propulsion, where matter and antimatter annihilate to produce energy with perfect efficiency. Even with perfect efficiency, reaching high fractions of light speed requires carrying enormous amounts of fuel, which itself must be accelerated. The rocket equation becomes brutal at relativistic speeds. Other proposals involve external energy sources, laser propulsion, where powerful lasers from Earth or from solar orbit push on light sails, could in principle accelerate spacecraft to significant fractions of light speed without requiring onboard fuel for the acceleration phase. Breakthrough Starshot, a research program announced in 2016, has proposed using this technique to send gram-scale probes to Alpha Centauri at about 20% of light speed, which would make the journey in about 20 years. Whether this ambitious proposal can be realized remains to be seen. Even at 20% of light speed, time dilation is only about 2%. The probes would experience about 20 years, minus about 5 months compared to Earth time. Not dramatic, but it demonstrates the principle. Time dilation also affects how we think about the lifespan of the universe. From the perspective of a photon, a particle of light, traveling at the speed of light, time dilation is infinite. The photon experiences no passage of time at all. It's emitted and absorbed in the same instant from its own perspective. even if it travels across the entire observable universe over billions of years from our perspective. This is why photons don't decay. Decay requires time passing in the particle's reference frame. For a photon, no time passes, so it never ages and never decays. For massive particles traveling at speeds very close to but not quite equal to light speed, time dilation can extend their effective lifetimes almost indefinitely. Cosmic rays, high-energy particles from distant supernovae or other astrophysical sources, can travel across the galaxy for tens of thousands of years by our clocks while experiencing only minutes or hours or days of their own proper time. This raises interesting questions about the deep future of the universe. As the universe expands and accelerates, galaxies recede from each other at ever-increasing speeds. Eventually, distant galaxies will recede faster than light can travel relative to us, not because they're moving faster than light through space, but because space itself is expanding between us and them. Light from those galaxies will become infinitely redshifted. Time in those galaxies, from our perspective, will slow and eventually appear to stop. The galaxies will fade from view, disappearing beyond what's called the cosmic event horizon. We'll be unable to see them or communicate with them ever again. Different parts of the universe will be causally disconnected, each with its own separate history. In this distant future, an observer in one galaxy cluster would see their local group of gravitationally bound galaxies, illuminated by starlight and other radiation. But beyond that, only darkness, an expanding void where the rest of the universe used to be. Each galaxy cluster would be like an island universe, alone in an infinite ocean of space. All of this is connected to time dilation and the properties of space-time described by general relativity. The universe's expansion, the cosmic event horizon, the ultimate fate of distant structures, all follow from the same principles that explain why GPS needs relativistic corrections and why flying clocks around the world on airplanes show measurable time differences. Current research is also exploring connections between time dilation and quantum field theory. In quantum field theory, particles are excitations of underlying fields that fill all of space. These fields interact and evolve according to relativistic quantum mechanics. Time dilation affects how these fields behave in different reference frames and in different gravitational environments. One fascinating question is whether quantum effects could alter time dilation in subtle ways. Classical general relativity predicts specific time dilation formulas, but general relativity is a classical theory, not a quantum theory. At some level, quantum effects should modify its predictions. These modifications would be incredibly tiny for normal circumstances, far below anything we can currently measure, but in extreme situations near the Planck scale where quantum effects become strong, quantum corrections to time dilation might become important. Understanding these corrections requires a theory of quantum gravity, which physicists are still working to develop. String theory, loop quantum gravity, and other approaches to quantum gravity make different predictions about how time might behave at the smallest scales. Testing these predictions experimentally is extraordinarily difficult because the effects are so small. But some researchers hope that ultra-precise atomic clocks or other quantum sensors might eventually detect tiny deviations from classical general relativity that could distinguish between different quantum gravity theories. Another cutting-edge area involves theoretical proposals for using time dilation in quantum information processing. Quantum computers leverage quantum superposition and entanglement to perform certain calculations much faster than classical computers. But quantum states are fragile. They decohere quickly when disturbed by their environment. Some researchers have proposed using time dilation to protect quantum information. If you could put a quantum computer in a strong gravitational field or accelerate it to high speed, time dilation might, in theory, slow the decoherence process from the perspective of an outside observer. This could potentially allow longer computation times before errors accumulate. This remains highly speculative and faces enormous practical challenges, but it illustrates how time dilation connects to many areas of physics and technology, from GPS to quantum computing to the ultimate fate of the universe. Let me take a moment to emphasize just how thoroughly time dilation has been tested and confirmed. It's not a theoretical speculation. It's not a mathematical curiosity. It's observed reality, verified in dozens of different ways with extraordinary precision. The Hafele-Keating experiment measured it with flying atomic clocks in 1971. GPS demonstrates it every day in billions of devices. Muon experiments confirmed it starting in 1941 and continuing to the present. Particle physics experiments see it routinely in particle decays. The Pound-Rebka experiment measured gravitational time dilation in 1959. Modern optical atomic clocks have measured it over height differences as small as 1 millimeter. Observations of binary pulsars, pairs of neutron stars orbiting each other at high speeds in strong gravitational fields, show time dilation effects. The famous Hulse-Taylor binary pulsar, discovered in 1974, provided the first indirect evidence for gravitational waves because energy loss from gravitational wave emission was causing the orbit to decay exactly as predicted by general relativity, including all time dilation effects. Observations of stars orbiting the supermassive black hole at our galaxy's center show time dilation and gravitational redshift. Images of black hole event horizons match predictions, including time dilation effects. Cosmological observations of distant supernovae show time dilation from the expansion of the universe. Every test confirms Einstein's predictions. There are no confirmed deviations. Time dilation is as thoroughly established as any result in physics. What does all this mean for our everyday experience? For most of us, most of the time dilation is negligible. The speeds we move at and the variations in Earth's gravitational field we experience are small enough that the effects are far below human perception, but they're real. Time is passing slightly differently for you, depending on your elevation and your velocity. If you live on the ground floor of a building, time passes slightly slower for you than for someone on the 10th floor. The difference is tiny, only about 1 part in 10 to the 16th over a year, for a height difference of 30 meters, but it's real. If you drive east on a highway, time passes slightly slower for you than if you were stationary, because you're moving faster relative to Earth's center. If you drive west, time passes slightly faster. The effects are absurdly small, unmeasurable without atomic clocks, but they exist. Every time you use GPS, you're relying on corrections for time dilation. The satellite signals you receive have been adjusted for the relativistic effects of velocity and altitude. Without those corrections, GPS wouldn't work. Pilots and frequent flyers age fractionally less than people who stay on the ground because they spend time at high speeds and high altitudes. The effect is incredibly tiny, less than a microsecond over a lifetime of flying. But it's there. Astronauts age slightly less during their time in orbit. The handful of humans who have spent long durations on the International Space Station have aged milliseconds less than they would have on Earth. Cosmonaut Sergei Krikalev, who spent a total of 803 days in space over his career, aged about 23 milliseconds less than he would have on the ground. He's the human who has traveled farthest into Earth's future by that tiny margin. What time dilation tells us, ultimately, is that the universe is stranger than our everyday experience suggests. Time is not absolute. It's not a universal constant flowing at the same rate everywhere. It's flexible. It's relative. It's depends on motion and gravity. This challenges our intuition. We evolved to navigate the world at human speeds and human scales. Our brains are wired to expect time to be universal, but the universe doesn't care about our intuitions. At high speeds and in strong gravity, time behaves in ways that seem bizarre to us, but are perfectly natural consequences of how space-time actually works. Einstein's theories of relativity are now over a century old. Special relativity was published in 1905. General relativity in 1915. They've been tested and confirmed countless times. They're the foundation of modern physics. Everything from GPS to particle accelerators to cosmology depends on them being correct. Yet they still seem strange and counterintuitive. The idea that time passes at different rates for different observers, that simultaneity is relative, that you could age less than someone else by traveling at high speed. These notions still feel alien even to physicists who work with them daily. That's because they're so far outside everyday experience. But they're real. They're true. They're how the universe actually works. As we develop more advanced technology, time dilation will become increasingly important. Faster computers and communication networks require better time synchronization, which means accounting for relativistic effects, even over short distances. Future space-based systems, whether satellites, space stations, or lunar bases, will need precise relativistic corrections. If we ever develop the capability for interstellar travel, time dilation will be central to mission planning. Crew aging, Earth time versus ship time, the trade-offs between speed and energy consumption, all will involve careful relativistic calculations. Even in less exotic applications, ultra-precise timing is becoming more important. Financial markets operate at microsecond timescales. High-frequency trading systems need synchronized clocks. Distributed computing systems need coordinated timing. As precision increases, relativistic effects that were once negligible become relevant. Time dilation also reminds us that the universe is comprehensible. It follows laws. Those laws can be discovered, tested, and applied. Einstein figured out the mathematics of time dilation by thinking carefully about the consequences of light having a constant speed. His predictions, made with pencil and paper over a century ago, have been confirmed to extraordinary precision by modern experiments. This is the power of theoretical physics. By reasoning carefully about how the world must work, we can predict phenomena beyond our direct experience. Then we can test those predictions, refining our understanding. The fact that relativity has passed every test shows that our mathematical descriptions of nature are capturing something real about how the universe operates. Understanding time dilation also opens up philosophical questions that haven't been fully resolved. If time is relative, if different observers can disagree about time intervals and simultaneity, what does that mean for free will, for causality, for the nature of consciousness? These are deep waters. Some philosophers argue that relativity supports a deterministic view of the universe, where all events are laid out in a four-dimensional space-time block, where past, present, and future all exist equally, and the passage of time is an illusion. Others argue that quantum mechanics introduces fundamental randomness that preserves free will, even in a relativistic universe. The debate continues. What's clear is that time is not what common sense says it is. It's not a universal backdrop against which events unfold. It's part of the dynamic structure of space-time, affecting and affected by matter and energy. Massive objects warp space-time around them, slowing time in their vicinity. Moving objects experience time differently than stationary ones. This interconnection of space, time, matter, and energy is the essence of relativity. Nothing exists in isolation. Everything is connected through the geometry of space-time. Looking forward, time dilation will remain a crucial concept as we push the boundaries of physics. Future gravitational wave detectors, like the proposed space-based LISA mission, would observe systems where time dilation effects are extreme if successfully deployed. Neutron stars and black holes merging create regions of intense gravity where time flows radically differently than in empty space. Understanding these systems requires precise modeling of time dilation. The laser interferometer space. Antenna LISA, currently planned for launch in the 2030s, would consist of 3 spacecraft flying in formation, separated by 2.5 million kilometers. If realized, these spacecraft would detect gravitational waves from massive systems like supermassive black hole mergers, events where time dilation becomes extraordinary. When 2 black holes orbit each other in the final moments before collision, the regions of space-time near them become so warped that time essentially stops at their event horizons, while the orbital dynamics happen on timescales of milliseconds. Dark matter and dark energy, the mysterious components that make up most of the universe's mass and energy, might interact with time in ways we don't yet understand. Some theories of modified gravity predict subtle deviations from general relativity's predictions for time dilation. Ultra-precise measurements might someday detect these deviations. The nature of dark energy itself could be connected to how time flows at cosmic scales. Dark energy appears to be causing the universe's expansion to accelerate. This acceleration affects how time passes at different cosmic epochs. In the distant future, as dark energy drives cosmic expansion faster and faster based on current models, the relationship between time in different parts of the universe would become increasingly complex. Some cosmological models suggest that dark energy might not be constant, but could vary over cosmic time. If this turns out to be true, the rate of cosmic expansion would change, which would affect cosmological time dilation. Future observations of distant supernovae and other cosmic standard candles might detect variations in time dilation that could reveal properties of dark energy we can't currently measure. Quantum gravity, the still undeveloped theory that would unite quantum mechanics and general relativity, could modify our understanding of time at the smallest scales. Some theoretical frameworks suggest time might be emergent from more fundamental quantum structures. It might even be quantized, coming in discrete units, rather than being continuous. These remain speculative ideas, but time dilation measurements with future ultra-precise clocks could potentially provide clues. In loop quantum gravity, one theoretical approach to quantum gravity, space-time itself is proposed to be quantized. Area and volume would come in discrete units at the Planck scale, roughly 10 to the minus 35 meters. If space is quantized in this way, time might be too. The Planck time, about 10 to the minus 44 seconds, could represent a fundamental tick of a cosmic clock, the smallest meaningful time interval, though this remains unproven. String theory, another approach to quantum gravity, describes particles as tiny vibrating strings. Time in string theory can behave in ways that differ from our everyday experience. Some string theory models include extra dimensions of space beyond the three we experience. Time might have structure we don't perceive at everyday scales. The mathematics of string theory modifies Einstein's equations in subtle ways that could, in principle, be detected with sufficiently precise measurements of time dilation, though no such deviations have been observed. One prediction from some quantum gravity theories is that time dilation might have quantum corrections. In classical general relativity, time dilation is completely determined by velocity and gravitational potential. But quantum effects might introduce tiny random fluctuations in the rate at which time passes. These fluctuations would be incredibly small, far below current measurement capability. Future atomic clocks might eventually be sensitive enough to test these ideas. If we could detect quantum fluctuations in time itself, it would revolutionize physics. It would provide the first direct experimental evidence for quantum gravity. It would show that space-time, at the smallest scales, behaves quantum mechanically, subject to Heisenberg's uncertainty principle. The implications would be profound for our understanding of black holes, the Big Bang, and the fundamental nature of reality. The study of time dilation over the past century shows science at its best. A brilliant insight from pure reasoning, testable predictions, careful experiments confirming those predictions, practical applications benefiting society, and ongoing research pushing into new frontiers. This is how we expand human knowledge. Consider the arc of discovery. In 1905, Einstein proposed that time is relative based on thinking about the constancy of light speed. The idea was radical, contradicting centuries of thought about absolute time. Many physicists were skeptical, but the mathematical predictions were clear and testable. Early tests came from observations of particle physics. The muon lifetime measurements in the 1940s provided strong evidence. By the 1950s, more sophisticated particle accelerator experiments were confirming time dilation with increasing precision. Every high-energy physics experiment since has been consistent with relativity. The Pound-Rebka experiment in 1959 and 1960 brought gravitational time dilation into the laboratory. Measuring an effect of parts per quadrillion required experimental ingenuity and precision. The fact that it worked, that Einstein's prediction held up, was a triumph. The Hafele-Keating experiment in 1971 made time dilation tangible in a new way. You could put clocks on commercial airplanes and measure the effect. This wasn't a specialized particle physics experiment requiring million-dollar equipment. It was atomic clocks flying on regularly scheduled flights. The accessibility made the result more visceral somehow, more real. GPS, developed in the 1970s and 1980s and fully operational in the 1990s, turned time dilation from an interesting physics result into a practical necessity. Millions of people now use GPS daily. The relativistic corrections aren't optional or theoretical. They're required for the system to function. This demonstrates beyond any doubt that relativity is true and has measurable consequences in the everyday world. Modern optical lattice clocks, developed in the 2000s and 2010s, have pushed precision to extraordinary levels. The ability to measure time dilation over millimeter height differences shows just how far the technology has advanced. These clocks are tools for testing the foundations of physics at unprecedented precision. They might reveal new phenomena, deviations from general relativity that point toward quantum gravity or other new physics. Throughout this century of progress, every experiment has confirmed Einstein's predictions. Relativity has passed every test. This doesn't mean it's the final word. We know general relativity is incomplete because it doesn't include quantum mechanics. At some level, it must be replaced by a more fundamental theory, but the more fundamental theory will have to reproduce all of general relativity's successful predictions in the regimes we've tested. Time dilation, as described by Einstein's equations, is thoroughly established experimental fact. The precision of modern tests is almost unbelievable. Optical lattice clocks can measure fractional frequency differences at the level of 1 part in 10 to the 18th. That means if two clocks start synchronized, after running for the age of the universe about 14 billion years, they would differ by less than 1 second. This precision allows gravitational time dilation to be measured over height differences comparable to the thickness of a sheet of paper. Think about what this means. Earth's gravitational field decreases with altitude. Move higher and you experience slightly weaker gravity, which makes time pass slightly faster. The effect is about 1 part in 10 to the 16th per meter of height at Earth's surface. For 1 millimeter of height difference, it's 1 part in 10 to the 19th. These are numbers so small they defy intuition, yet we can measure them. We can put two atomic clocks 1 millimeter apart vertically and detect that the upper clock ticks faster than the lower one by this tiny fraction. This demonstrates both the reality of gravitational time dilation and the extraordinary capability of modern measurement. Technology. What practical applications might emerge from this capability? One possibility is relativistic geodesy, using ultra-precise clocks to map Earth's gravitational field with centimeter-level height resolution. Gravity varies slightly from place to place due to variations in rock density, underground water, tectonic structure, and other factors. Traditional geodesy uses satellite measurements and gravity meters, but portable optical atomic clocks could make direct measurements of gravitational potential differences, providing complementary data. This could be useful for geology, hydrology, and monitoring of natural hazards. Changes in groundwater levels alter the local gravitational field slightly. Magma movement beneath a volcano changes the field. Tectonic strain accumulation before an earthquake might produce detectable changes. Ultra-precise time measurements could, in principle, detect these effects. Portable atomic clocks could also be used for fundamental physics tests. By moving clocks to different locations and comparing them, physicists could search for subtle variations in fundamental constants or deviations from general relativity's predictions. If a constant, like the fine structure constant, varies from place to place or over time, atomic clock comparisons might detect it. There's also the possibility of using time dilation for applied problems. Precision timing is becoming increasingly important for telecommunications, computing, and financial markets. As these systems become faster and more distributed, relativistic effects that were once negligible become relevant. Understanding and accounting for time dilation will be necessary for next generation's ultra-high-speed networks. Let's delve deeper into the twin paradox because it's one of the most famous and sometimes misunderstood aspects of time dilation. The scenario is simple. Two twins, Alice and Bob, start together on Earth. Bob boards a spacecraft and travels to a distant star at high speed, then returns. When he arrives back, he's younger than Alice. He experienced less time during the journey. From Earth's perspective, this makes sense. Bob was moving at high speed, so his clock ticked slower due to time dilation. Simple enough. But what about Bob's perspective? From his point of view, he was at rest in the spacecraft, and it was Earth and Alice that were moving away at high speed. Shouldn't Alice's clock tick slower from Bob's perspective? When they reunite, shouldn't Alice be younger? This seeming contradiction is the twin paradox. It's not actually a paradox because the situation is not symmetric. Bob accelerates when he starts the journey, decelerates, and accelerates again when he turns around at the distant star, and decelerates when he arrives back at Earth. Alice experiences no such accelerations. She remains in an inertial reference frame the whole time. Acceleration breaks the symmetry. During the acceleration phases, Bob's reference frame is not inertial. Special relativity, which describes time dilation for inertial frames, doesn't directly apply. To fully analyze what Bob experiences, you need to use general relativity, which handles accelerated motion. The resolution becomes clear when you carefully track what happens during the turnaround. Imagine Bob is traveling at 80% of light speed to a star 8 light years away. From Earth's perspective, the outbound journey takes 10 years. The return journey also takes 10 years. Total elapsed time on Earth is 20 years, but from Bob's perspective, his clock ticks slower by the Lorentz factor, which at 80% of light speed is about 1.67. So Bob experiences the outbound journey as taking about 10 divided by 1.67, roughly 6 years. The return journey also takes 6 years. Bob ages 12 years, while Alice ages 20 years. But what does Bob see? During the outbound journey, Bob sees Alice and Earth receding. From his perspective, Alice's clock should be ticking slower. If he could, watch Alice through a powerful telescope, accounting for light travel time, he would indeed see her aging more slowly than himself during this phase. However, during the turnaround, something dramatic happens. When Bob fires his rockets to turn around, he experiences strong acceleration. From his accelerating reference frame, Alice's clock suddenly appears to jump forward. The effect is similar to how gravitational time dilation works. Acceleration and gravity are equivalent according to the equivalence principle, and during acceleration, there's an apparent gravitational field in the accelerated frame that makes distant clocks appear to tick faster. During the brief turnaround period from Bob's perspective, Alice ages many years. Her clock appears to race forward. This more than compensates for the slower ticking he observed during the outbound journey. On the return journey, Alice's clock again appears to tick slower than Bob's, just as on the outbound leg. But the jump during turnaround means that overall, Alice ages more than Bob, even from Bob's perspective. The key is that the turnaround acceleration is experienced by Bob, not Alice. This physical asymmetry resolves the apparent paradox. The twin who accelerates ages less. The twin who remains in an inertial frame ages more. This had been directly tested with atomic clocks. The 1977 experiment at CERN stored muons in a magnetic storage ring. The muons were constantly accelerating as they traveled in a circle. Despite the acceleration, their lifetimes were extended by time dilation exactly as predicted. The muons aged less than they would have if stationary, even though they were accelerating. More recent tests have flown atomic clocks on airplanes, which involves takeoff and landing accelerations, as well as the constant centripetal acceleration from flying on a curved path over Earth's spherical surface. Every test confirms that the accelerating clock ages less, as predicted. This means the twin paradox scenario could actually be realized with current technology, though the effect would be tiny. If you put two synchronized atomic clocks in different locations, flew one on a long airplane journey while the other stayed on the ground, and then reunited them, the traveling clock would show less elapsed time. The difference might be only nanoseconds, but it would be measurable and would match the relativistic predictions. For human twins to experience a significant age difference, one would need to travel at a substantial fraction of light speed. At 90% of light speed on a round trip to a star 10 light years away, the traveling twin would age about 9 years, while the earthbound twin aged about 22 years. The difference would be dramatic and undeniable. No human has ever traveled at anything close to such speeds. Our fastest spacecraft, the Parker Solar Probe, reaches speeds of about 700,000 kilometers per hour at its closest approach to the Sun, about 0.06% of light speed. At this speed, time dilation is less than 1 part per billion. Astronauts have experienced slightly larger effects by orbiting Earth at 28,000 kilometers per hour for extended periods, but the most any human has aged differently from Earth-bound people is a few tens of milliseconds. For relativistic travel to become practical, we would need breakthrough propulsion technologies. Chemical rockets can't get us to significant fractions of light speed. The energy requirements are too high, and the fuel mass required becomes prohibitive. Nuclear propulsion offers higher energy density, but still falls far short of what would be needed. Antimatter-matter annihilation provides perfect energy conversion, releasing all the rest mass as energy according to Einstein's equation, E equals mc squared. In principle, antimatter propulsion could accelerate a spacecraft to high relativistic speeds, but we can barely produce and store tiny amounts of antimatter with current technology. Scaling up to the quantities needed for a spaceship drive remains far beyond current capabilities, and may face fundamental practical barriers. Other speculative ideas include fusion ramjets that would scoop up interstellar hydrogen and fuse it for propulsion, or laser-pushed light sails driven by powerful laser arrays in the solar system. These remain theoretical proposals. The engineering challenges are immense, but they're not physically impossible. The laws of physics allow relativistic space travel in principle. Whether it's practically achievable is an engineering question that remains unanswered. If we ever achieve such capabilities, time dilation will become a central consideration for mission planning. Long interstellar voyages would see dramatic time dilation effects. Crews might age only years or decades during journeys that take centuries or millennia from Earth's perspective. They'd return to find Earth transformed, their friends and family long dead, society completely changed. This would create profound psychological and social challenges. Science fiction has explored these scenarios extensively. Ursula K. Le Guin's novel, The Dispossessed, examines the social implications. Tau Zero by Poul Anderson depicts a spacecraft that continues accelerating until time dilation becomes so extreme that the crew witnesses the end of the universe. These stories explore the human dimensions of time dilation in ways that pure physics cannot. But they're based on real physics. The time dilation effects described in these stories, while perhaps exaggerated for dramatic effect, are qualitatively accurate. If we ever build spacecraft capable of relativistic speeds, the crews really will experience what these stories describe. They really will return younger than they should be, having skipped through time into the future. Let's explore gravitational time dilation near different types of astronomical objects to understand the full range of effects. We've discussed black holes, where time dilation becomes infinite at the event horizon. But what about other extreme objects? Neutron stars are the remnants of massive stars that exploded as supernovae. The core, compressed beyond the point where electron degeneracy pressure can support it, collapses until neutrons themselves provide support through degeneracy pressure. The result is an object about 20 kilometers in diameter containing 1 to 2 solar masses. The density is roughly the same as an atomic nucleus, about 1 billion metric tons per cubic centimeter. Gravity at a neutron star's surface is intense, about 200 billion times stronger than Earth's. Time dilation is significant, though the exact amount depends on the neutron star's mass and radius. For a typical neutron star with about 1.4 solar masses and a radius around 12 to 20 kilometers, clocks on the surface tick roughly 10 to 20% slower than clocks far from the star. For more massive neutron stars approaching the theoretical maximum mass limit of about 2 to 2.5 solar masses, time dilation can become substantially more extreme, with surface clocks running anywhere from 30 to 50% slower, or even more for neutron stars very close to collapsing into black holes. Some neutron stars rotate extremely rapidly. These are called pulsars. They emit beams of radiation from their magnetic poles, and as they rotate, we see pulses of radiation, hence the name. The fastest pulsars rotate over 700 times per second. Their surfaces are moving at significant fractions of light speed, adding velocity time dilation on top of gravitational time dilation. For an observer on the surface of a rapidly rotating pulsar at the equator, both effects combine. Time passes much more slowly than for a distant observer. The combined time dilation factor can reach values of 2 or more. This has observable consequences. The radiation we detect from pulsars is time dilated. The pulses we observe are stretched out in time compared to the emission in the pulsar's reference frame. White dwarfs, less extreme than neutron stars, also produce measurable gravitational time dilation. A white dwarf is the remnant of a medium-mass star like our Sun. After the star exhausts its fuel and sheds its outer layers as a planetary nebula, the core remains. Electron degeneracy pressure, the quantum mechanical pressure from electrons packed as tightly as the Pauli exclusion principle allows, supports the star against gravity. A typical white dwarf has about the mass of the Sun compressed into a sphere about the size of Earth. Gravity at the surface is about 100,000 times Earth's gravity. Time dilation is about 1 part in 10,000. A clock on a white dwarf's surface ticks about 0.01% slower than a clock far away. This effect has been observed spectroscopically. Light from white dwarfs is gravitationally redshifted. Spectral lines are shifted toward longer wavelengths compared to the same lines produced in a laboratory on Earth. By measuring this redshift, astronomers can determine the white dwarf's mass and radius because the redshift depends on the gravitational potential at the surface, which in turn depends on the mass-to-radius ratio. The first white dwarf discovered, Sirius B, the companion to the bright star Sirius, was found to have a gravitational redshift consistent with its mass and size. This was one of the early confirmations of general relativity's predictions for gravitational time dilation in an astrophysical context. Our own Sun produces a small gravitational time dilation effect. At the Sun's surface, gravity is about 28 times Earth's gravity. Time passes about 1 part per million, slower there than far from the Sun. This is small but measurable with spectroscopy. Solar spectral lines are slightly redshifted compared to the same lines produced in laboratories on Earth. The effect was measured in the early 20th century and confirmed general relativity's predictions. Even Earth produces gravitational time dilation. At Earth's surface, compared to infinity, time passes slower by about 1 part in a billion. This is the effect that GPS satellites must account for. The satellites, being 20,000 kilometers higher, experience weaker gravity, and their clocks tick faster. The time dilation at Earth's surface has been verified in multiple ways. The Pound-Rebka experiment measured it over a 22-meter height difference in a tower. Modern atomic clocks have measured it over height differences of centimeters and millimeters. The effect is thoroughly confirmed and is now used as a tool for precise measurement of elevation and gravitational potential. Jupiter, the largest planet in our solar system, also produces measurable gravitational time dilation. At Jupiter's cloud tops, time passes about 2 parts per billion, slower than far from Jupiter. This is small, but spacecraft mission planners must account for it when designing deep space navigation and timing systems. The effect becomes more significant for hypothetical objects. A planet with Earth's density but much larger radius would have stronger surface gravity and more time dilation. If you could build a planet the size of Jupiter but with Earth's density, surface gravity would be about 2.5 times Earth's, and time dilation would be about 3 parts per billion. The most extreme gravitational time dilation possible without forming a black hole, occurs at the surface of the largest possible neutron star, right at the point where it would collapse to form a black hole. For a non-rotating neutron star, this limit is reached at about 2 to 2.5 solar masses, depending on the equation of state of neutron star matter. At the surface of such a maximal neutron star, time dilation could reach factors of 2 or more. An hour on the surface would correspond to over 2 hours far away. If such a maximal neutron star were to accrete just a bit more mass, it would collapse and form a black hole. The event horizon would appear at a specific radius, the Schwarzschild radius. Inside this radius, time dilation from the perspective of distant observers becomes infinite. The object has crossed the threshold into becoming a black hole. This transition is one of the most dramatic events in the universe. From the perspective of distant observers, the collapse appears to slow and freeze as the surface approaches the Schwarzschild radius. The collapsing matter becomes increasingly redshifted and dim, asymptotically approaching but never quite reaching the event horizon. From the perspective of the collapsing matter itself, the collapse continues right through the Schwarzschild radius in finite proper time, and the matter continues falling toward the singularity at the center. These extreme scenarios illustrate the range of time dilation effects in the universe, from the tiny effects at Earth's surface to the infinite dilation at a black hole event horizon. Time itself is flexible and responsive to the distribution of mass and energy. Everywhere you look in the universe, time is flowing at different rates. The cosmic symphony of time is not a single universal tempo, but a complex polyphony where different regions of space keep different times. The measurement techniques that have allowed us to verify time dilation deserve deeper exploration because they represent some of the most precise measurements ever made in physics. Let's look at how modern atomic clocks actually work and how they've evolved to their current extraordinary precision. The first atomic clocks, developed in the late 1940s and 1950s, used cesium atoms. They worked by measuring the microwave frequency at which cesium atoms transition between different hyperfine states, states distinguished by the orientation of nuclear and electron spins. This transition frequency is extremely stable, about 9.19 billion cycles per second, and forms the basis of the definition of the second in the International System of Units. The current official definition, adopted in 1967, states that 1 second is the duration of 9,192,631,770 periods of the radiation corresponding to the transition between two hyperfine levels of the ground state of cesium-133. This definition makes the second a fundamental unit based on atomic physics rather than on astronomical observations as it was previously. Cesium atomic clocks work by preparing cesium atoms in one hyperfine state, exposing them to microwave radiation, and detecting how many atoms transitions to the other state. By carefully tuning the frequency of the microwave radiation to maximize the transition rate, you can lock onto the precise resonant frequency. This frequency then serves as an extremely stable time base for the clock. Modern cesium fountain clocks use a clever technique. They launch cesium atoms upward in a vertical tube, creating an atomic fountain. As the atoms rise and fall under gravity, they spend more time interacting with the microwave field, allowing more precise measurement of the resonant frequency. This technique, along with other improvements like laser cooling to reduce the atom's thermal motion, allows cesium fountain clocks to achieve fractional frequency uncertainties below 1 part in 10 to the 15th power. That level of precision means the clock would neither gain nor lose 1 second in about 30 million years. That's extraordinary accuracy. But optical lattice clocks, the current state of the art, are even better. Optical lattice clocks use optical transitions between electronic energy levels that absorb or emit visible or near visible light rather than microwaves. These transitions have frequencies hundreds of thousands of times higher than microwave transitions. Higher frequency allows finer time resolution and potentially better stability. The atoms, typically strontium, ytterbium, or calcium, are trapped in an optical lattice, a standing wave pattern created by counter-propagating laser beams. The atoms sit at the nodes of this standing wave, where they experience minimal perturbation from the trapping light. This allows their natural transition frequencies to be measured with minimal distortion. A highly stabilized laser is tuned to the optical transition frequency. The atoms are prepared in their ground state, then exposed to the laser. By measuring what fraction of atoms transition to the excited state, you can determine how close the laser frequency is to the true atomic transition frequency. Sophisticated servo systems continuously adjust the laser frequency to stay locked to the atomic transition. The stability of the best optical lattice clocks is almost incomprehensible. Fractional frequency uncertainties below 1 part in 10 to the 18th power have been achieved. This means the clock would be accurate to within 1 second over the entire age of the universe, about 14 billion years. With such precision, these clocks can detect the gravitational time, dilation from raising them just 1 centimeter. They can sense the disturbance from someone walking nearby, because the person's mass slightly alters the local gravitational field. They're sensitive to general relativistic effects that were completely inaccessible to measurement until this decade. The development of these ultra-precise clocks has required solving countless technical challenges. Laser systems must be stabilized to extraordinary levels. Environmental perturbations like temperature fluctuations, vibrations, and electromagnetic fields must be minimized. The atomic physics must be understood in exquisite detail to account for all possible sources of frequency shifts. One challenge is the blackbody radiation shift. Any object at finite temperature emits thermal radiation. This radiation creates an oscillating electromagnetic field that shifts atomic energy levels slightly. The size of the shift depends on temperature. For optical atomic clocks, the blackbody shift can be significant. To minimize it, the atomic sample is surrounded by a carefully temperature-controlled shield, whose blackbody radiation field is well characterized. Another challenge is collisional shifts. Even in ultra-high vacuum, atoms occasionally collide with each other or with residual background gas. These collisions can perturb the atomic transition frequencies. By working with ultra-cold atoms and carefully managing the atomic density, these effects can be controlled and measured. Magnetic and electric fields also perturb atomic energy levels through the Zeeman and Stark effects. The clock must operate in carefully controlled field environments. Any stray fields must be characterized and accounted for. The precision required is remarkable. Magnetic fields must be stable and uniform, to better than a nanotesla. about 1/1000th of Earth's magnetic field. Gravity itself must be characterized. Since the clock is sensitive to gravitational time dilation, any uncertainty in the gravitational potential at the clock's location introduces uncertainty in the time measurement. For the most precise clocks, Earth's tides, which slightly change the local gravitational field as the moon and sun's pull varies, must be accounted for. Even the gravitational pull of atmospheric pressure changes can matter. All these effects and more must be carefully measured, modeled, and corrected. The systematic uncertainty budget for a state-of-the-art and optical lattice clock includes dozens of contributions, each characterized to levels that would have been unthinkable decades ago. The fact that physicists can achieve such control and precision is a testament to experimental ingenuity and dedication. These clocks are not just physics experiments, they're becoming practical tools. Proposals exist to use networks of optical lattice clocks connected by fiber optic links to create a global time and frequency standard that could surpass current capabilities. Such a network could enable new applications in navigation, communications, and fundamental physics research. Portable optical clocks are being developed that could be transported to different locations for field measurements. If successfully deployed, these could be used for relativistic geodesy, measuring gravitational potential differences to determine elevations with centimeter precision or to detect underground mass anomalies. They could potentially monitor volcanic activity by detecting changes in gravity from magma movement, or track groundwater levels by sensing gravitational changes from water mass redistribution, though these applications remain largely theoretical. In fundamental physics, optical lattice clock networks could search for variations in fundamental constants. If constants like the fine structure constant or the ratio of atomic masses change over time or vary with position, comparisons between distant optical clocks might detect these changes. Such variations would indicate new physics beyond the standard model, though no evidence for variation has been found so far. They could also test the equivalence principle with unprecedented precision. The equivalence principle states that all objects fall at the same rate in a gravitational field, regardless of their composition. By comparing clocks based on different atomic species in different locations, physicists can test whether different forms of bound energy respond identically to gravity. Any violation would be revolutionary, though all tests to date have confirmed the equivalence principle. Looking at the historical development of our understanding of time gives perspective on just how radical Einstein's insights were. Before relativity, the Newtonian view of absolute time was unchallenged for over 200 years. Newton wrote that absolute, true, and mathematical time, of itself and from its own nature, flows equably without regard to anything external. Time was a universal backdrop, the same for all observers. This view matched everyday experience perfectly. Time seemed absolute. Clocks might run fast or slow due to imperfections in their mechanisms, but true time itself flowed uniformly. The idea that time might actually pass at different rates for different observers would have seemed absurd. Yet cracks in the Newtonian edifice began appearing in the 19th century. James Clerk Maxwell's equations for electromagnetism, formulated in the 1860s, predicted that light was an electromagnetic wave traveling at a specific speed. but Maxwell's equations didn't specify what that speed was measured relative to. Physicists assumed light traveled through a medium called the luminiferous ether, just as sound travels through air. The speed of light in Maxwell's equations would be the speed relative to the ether. If you moved through the ether, you should measure different light speeds depending on your motion. The Michelson-Morley experiment in 1887 tested this. Albert, Michelson, and Edward Morley built an extraordinarily sensitive interferometer to detect Earth's motion through the ether. As Earth orbits the Sun, its velocity direction changes throughout the year. At different times of year, Earth should be moving in different directions relative to the ether. The speed of light should vary accordingly, but it didn't. No matter when they conducted the experiment, no matter Earth's orbital position, the speed of light was always the same. The result was puzzling. Many physicists tried to explain it away. Perhaps the ether was dragged along by Earth. Perhaps the laboratory apparatus contracted in the direction of motion in just the right way to hide the effect. Hendrik Lorentz and George Fitzgerald independently proposed that moving objects actually do contract in their direction of motion by a factor that exactly compensates for the expected variation in light speed. The Lorentz-Fitzgerald contraction seemed ad hoc, a fix to save the ether theory rather than a deep physical insight. Einstein's breakthrough was recognizing that if you took the constancy of light speed seriously, as a fundamental principle rather than a mysterious coincidence, everything else followed. Time and space had to be relative. The Lorentz contraction was real, but it wasn't about motion through the ether. It was about how space and time themselves transformed between reference frames. Einstein's 1905 paper was remarkably short and direct. He assumed the principle of relativity, that physics is the same in all inertial frames, and the constancy of light speed. From these two postulates, he derived the Lorentz transformations that relate space and time, coordinates between different reference frames. Time dilation and length contraction emerged as necessary consequences. The paper had no references. Einstein was aware of the earlier experimental and theoretical work, but he approached the problem from first principles, thinking about how observers in different reference frames would measure space and time intervals. His approach was more philosophical and conceptual than mathematical, though the mathematics was rigorous. Once the concepts were clear, the scientific community's reaction was mixed. Some physicists immediately recognized the brilliance of Einstein's insights. Others were skeptical or hostile. The idea that time could be relative challenged fundamental assumptions about reality. It took years for relativity to be widely accepted. Experimental confirmation helped. The observation of muon lifetime, extension in cosmic rays, the measurement of time dilation in particle accelerators, the Pound-Rebka experiment, and other tests gradually convinced skeptics. By the 1960s, relativity was thoroughly established. Today, it's one of the most tested and confirmed theories in physics. General relativity's reception was similar but even more dramatic. Einstein spent nearly a decade developing the theory, from about 1907 to 1915. The mathematics of curved space-time using differential geometry and tensor calculus was difficult and unfamiliar to most physicists. The final field equations related the curvature of space-time to the distribution of mass and energy in a complex, nonlinear way. Einstein's first major prediction from general relativity was that light should be deflected by massive objects. During a total solar eclipse in 1919, British astronomer Arthur Eddington led expeditions to measure the positions of stars near the Sun. The stars appeared shifted compared to their normal positions, exactly as Einstein predicted. The deflection angle matched general relativity's prediction and differed from the Newtonian prediction by a factor of 2. The eclipse measurements made Einstein world famous overnight. Newspapers around the world proclaimed that space-time was curved, that Newton had been superseded, that a new era in physics had begun. This was partly due to the scientific importance of the result, but also to the historical context. The measurements were made just after World War I, and the fact that British scientists confirmed the theory of a German physicist was seen as a hopeful sign for international cooperation. Other predictions followed. The precession of Mercury's orbit, known since the 19th century but unexplained by Newtonian gravity, was precisely accounted for by general relativity. Gravitational redshift, though not measured terrestrially until 1959, was observed in white dwarf spectra in the 1920s. Gravitational lensing, where the gravity of a massive object focuses light from background sources, was observed in the 1970s and is now routinely used in astronomy. Gravitational waves, ripples in space-time from accelerating masses, were predicted by general relativity but not detected until 2015, a century after the theory was published. The Laser Interferometer, Gravitational Wave Observatory, LIGO, detected the merger of two black holes through the gravitational waves the event produced. This opened a new window on the universe and provided yet another confirmation of Einstein's theory. Throughout all these developments, time dilation has been central. It's one of the most direct and testable predictions of both special and general relativity. The progression from Einstein's theoretical prediction in 1905 through early indirect evidence in the 1940s to direct measurement in the 1950s and 1960s to routine application in GPS and other technologies today shows how scientific understanding develops through theory, experiment, and application. The philosophical implications remain deep and sometimes unsettling. Our intuitive sense that time is universal and absolute is wrong. Time is observer-dependent. Different observers can disagree about durations and even about the order of events in some cases. There is no universal now that all observers share. This challenges our notions of causality and free will. If the future already exists in some sense, laid out in the four-dimensional space-time manifold, does that mean our choices are predetermined? Most physicists and philosophers say no. The block universe view, where all of space-time exists equally, doesn't imply determinism in the sense of predictability. Quantum mechanics introduces fundamental randomness. Even in a block universe, the future might not be determined by the past. Others argue that the passage of time, the flow from past to future, is fundamental and cannot be reduced to geometry in space-time. The presentist view holds that only the present moment truly exists. Past events have occurred but no longer exist. Future events will occur but don't yet exist. Relativity complicates this view because different observers disagree about what constitutes the present moment. These are deep philosophical waters without clear answers. Physics tells us how time behaves, how it dilates and warps and flows at different rates. But what time fundamentally is, whether it's truly part of the fabric of reality or an emergent property or a feature of conscious experience, remains mysterious. What's clear is that time is far stranger than everyday experience suggests. The universe operates according to laws that often contradict common sense. Our intuitions, shaped by evolution to help us survive at human scales and speeds, are unreliable guides to reality at fundamental levels. This is both humbling and exhilarating. Humbling because it shows how limited our natural perceptions are. We perceive time as absolute because time dilation effects at everyday speeds are too small to detect. But perception is not reality. Reality includes effects we cannot directly sense. It's exhilarating because it demonstrates the power of human reason. By thinking carefully, by doing experiments, by building mathematical models, and testing them against observation, we can discover truths about nature that transcend our direct experience. We can understand time dilation not through intuition, but through intellect and evidence. This is the essence of science. We don't trust our gut feelings about how the world works. We test, we measure, we follow the evidence wherever it leads, even when it contradicts intuition. And what we discover is often more wonderful and strange than we could have imagined. Tonight we've journeyed from Einstein's revolutionary papers through experimental confirmations to modern ultra-precise measurements. We've seen how time dilation affects everything from cosmic rays in the atmosphere to GPS satellites in orbit to light escaping from black holes. We've explored the twin paradox, gravitational time dilation, and the implications for our understanding of reality. The fundamental lesson is this: time is not absolute. It's not a stage on which events play out. It's part of space-time, a flexible four-dimensional structure that can bend and warp and flow at different rates. Your experience of time depends on how fast you're moving and where you are in a gravitational field. This is strange. It's counterintuitive. It challenges the way we naturally think about the world. But it's true. The universe doesn't conform to our intuitions. We have to adjust our understanding to match what the universe actually is. And what the universe is, we've discovered, is far more subtle and intricate than he ever imagined. Time itself is relative. Past, present, and future may not be as distinct as they seem. Simultaneity depends on your reference frame. The passage of time you experience is not universal. These revelations from relativity theory, confirmed by over a century of experiments, show that reality is stranger and more wonderful than everyday experience suggests. The universe operates according to elegant mathematical laws that we can discover and test. Time dilation is one of those laws, woven into the very fabric of space-time. As you go about your day tomorrow, remember that time is passing slightly differently for you depending on your speed and altitude. The effects are tiny, unmeasurable without atomic clocks, but they're real. You're living in a universe where time itself is fluid and relative. If you found this exploration meaningful, please consider liking and subscribing to support the channel. Until next time, rest well knowing that you've glimpsed one of the deepest truths about the nature of reality. Time is not what you thought it was, and that makes the universe all the more extraordinary. Good night.